So this is a project with Jorge Vazquez and Sally Woodin, and we are funded to try to produce a ECOSTRESS sea surface temperature product that is compatible with the GHRSST standards. And just to refresh people's memories, ECOSTRESS is an instrument on the space station. It's a push-whisk radiometer. It uses mercury cadmium telluride sensors, and it has 5 infrared bands. The pixels are aggregated to about a 70 meter pixel size. The scenes are 5400 by 5600 pixels in size, and the instrument is fairly noisy. So this is a lot noisier than instruments like SLSTR and VIIRS. It has a revisit interval of sub-daily at latitudes like 50 north and south, and a 5-day revisit interval at the equator. And there have been something like 470,000 scenes acquired since it was launched. And the data are archived by USGS, LPDAC, and accessible from the NOAA search, or the NASA search system. And it's a precursor to future missions, Trishna, SPG, and LSTM. Temperature product production, the instrument has 2 black bodies, which are imaged on each swath. The temperatures of the black bodies are both warmer than sea surface temperatures, so that raises some potential issues with the use of this instrument for sea surface temperature products. The digitized data are saved in L1A files, and then there's a 2-point linear calibration based on the black bodies. In every swath, the calibrated radiances then are saved in L1B files. And then, because there were some calibration issues, a new production of the data has been created called Collection 2, and in that case, the original L1B radiance is adjusted with a gain and offset for every band. And then these are converted to brightness temperatures, and then geolocation is via Landsat database set, and then the swath data can be remapped, and USGS does this with the nearest neighbor mapping. The swaths overlap by about 30 pixels, so the pixel nearest to the geographic target may come from either end of the focal plane, and that raises some issues. And then JPL produces a skin temperature by a temperature emissivity separation algorithm. So why do we need on-orbit calibration? Well, it turns out that the Collection 1 skin temperatures have a cold bias of a little more than 1 degree Kelvin, and you can see that in this graph. So this is a bias relative to NOAA IQUAM, and so it's a large data set. This is 5 years worth of data in this graph. So another issue is that there's non-uniformity across the focal plane. So these graphs represent bias within the focal plane in a particular image. And so some pixels at one end of the focal plane may be running a little bit cold, others are right around the focal plane average, and then at the other end they can be a little bit cold. This becomes important because the way the instrument works, the instrument is traveling in this direction of the arrow, and swaths overlap. So one swath is acquired, and then the next swath overlaps it partly. And so what that means is that this particular pixel in a particular geographic location, the nearest one may come from this end of the focal plane, which is pretty much at the unbiased, or it may come from the other end of the focal plane, which is biased and biased cold. So the result of this is that we end up with a checkerboard pattern on the remapped data with cold pixels right next to hot pixels, next to cold pixels, and so on. And so this is a checkerboard artifact that turns up as a result of the non-uniformity in the focal plane. So this is something which has to be corrected if we're going to make a decent sea surface temperature, especially because the biases across the focal plane are as much as a 1/4 degree. So we've been looking at use of a number of infrared hyperspectral instruments as a way to calibrate the ECOSTRESS instrument, both at the scene level and at the individual pixel level on the focal plane. And the instruments we've been looking at are used by the Global Space-Based Intercalibration System as operational reference sensors. There's the cross-track infrared sounder on NOAA satellites. There's the infrared atmospheric sounding interferometer IASI on the METOP satellites from the European Union. And then there's the atmospheric infrared sounder on Aqua, which is not expected to last much longer because the orbit's decaying. And they all have moderately similar spectral resolution, and the pixel sizes are all about the same, 12 to 14 kilometers, which means you get about 10,000 to 30,000 ECOSTRESS pixels per individual retrieval from one of these sounders. So if we look at the spectral responses of these instruments, and we look at the band spectra for the various instruments, ECOSTRESS, Trishna, SPG, and LSTM. ECOSTRESS spectral responses of the individual channels are in blue. Trishna spectral responses are in orange. The SPG channels spectral responses are in black. And what you can see is that IASI covers the entire spectral range of all of these current and future high resolution instruments. Unfortunately, the CrIS instrument only covers part of the wave bands that are being imaged, that are planned to be imaged by the future missions, and only overlaps a few of the wave bands for the current instrument of ECOSTRESS. And VIIRS has even more gaps, and so it's even more problematic. But what this means is that IASI, which is on the METOP satellites, can serve as a reference instrument for basically harmonizing data from all of these future missions with the data from ECOSTRESS. And so this raises a major advance in being able to to harmonize data from these instruments, all of which have slightly different sensor types and modalities. So how do we do it? We use quasi-simultaneous overpass with acquisitions that are within 30 minutes of one another, and where in this case, the ECOSTRESS scene is near the midline of a sounder track. So here's the dots represent the sounder track. ECOSTRESS scene is down here near the British Isles, and the various sounder acquisitions are near from the midline of the sounder, and they overlap the ECOSTRESS image. We pick individual scenes and individual retrievals from fields of view from the sounder that match the zenith angles of the pixels within the the ECOSTRESS pixels that are within that field of view. And so there's a fairly tight constraint of the zenith angles, so that the direction of view and path of view is the same between both ECOSTRESS, or relatively the same between ECOSTRESS and the sounder. And then we only use scenes which have a brightness temperature standard deviation of less than ½ degree K. So when you do this comparison between the ECOSTRESS radiances and the CrIS radiances, what we find is that the ECOSTRESS radiances are very well, the ECOSTRESS radiances are all cold relative to the CrIS radiances. And so the one-to-one line is the dotted line on both of these graphs. The blue line is the JPL correction applied to the data. And you can see that the JPL correction does not lie on top of the scatter of points from the actual IASI comparison. So the JPL correction isn't really working. And so this indicates that the radiance biases are what we thought they were based on in-situ, and also that the JPL corrections that are now being applied in their newest collection are not correct. If we plot this as a bias, brightness temperature bias, using the IASI comparisons. In the 8.29 micron channel, the original collection 1 data were all biased cold, and the new collection 2 data are biased hot below 285 Kelvin and are biased cold below that. At 8.78, it's not quite as extreme a situation. That's the matchup is a lot better in terms of the correction applied, the JPL correction in collection 2, but it still doesn't completely fix it. At 9.2 microns, the new correction is still biased cold. It's just the slope with respect to temperature is the opposite of what it was before. At 10.49 microns, we have the same problem. We've got cold bias at high temperatures and warm bias at lower temperatures, and that's more extreme at 12.09 microns. Part of the problem is that the collection 2 bias correction is based on a comparison to in-situ data from Salton Sea, Lake Tahoe, and a few terrestrial sites. And they're based on 8 months of data when the instrument was collecting data from all 5 channels at the very beginning of the mission. And so those corrections are based on less data than in the case of the 8.29 and 9.2 micron channel, that's all the data they had for the correction. For the other channels, 8.78, 10.49, and 12.09, they had 42 months of data in order to build their corrections. So these 3 channels, the corrections are perhaps a little bit better, although that's questionable for the 12.09. So we still need to do corrections. We can't completely trust the JPL fix on the data. So if we look at the problem of non-uniformity in the focal plane, what we find is that the non-uniformities in the upper right-hand figure here represent the biases across the focal plane. And when we do a per pixel radiance correction, calculate corrections on the individual pixel in the focal plane basis, we end up with gain coefficients that are in the left-hand lower graph. And these numbers are very different from the gain correction in the in JPL collection 2, which is the black line at the bottom of the graph. There's an offset also in our correction factors, and they are in the right-hand graph, the lower part of the graph, and the JPL offset correction is at the top of the graph. So you can see there's quite a big difference between what we're getting using IASI and the average values that JPL is applying. But also the shape of the corrections kind of matches the pattern that you're seeing in the bias graph. So does it work? Here's an example of recalibration of pixels in a scene from Northwest Spain, where there's a very complicated pattern of upwelling filaments, which we can see in this brightness temperature image on the upper left of the slide. We can see all kinds of very fine detail. This is a 1 degree by 1.5 degree scene. If we look in greater detail, the lines on the left-hand edge of the left-hand graph represent the size of the next image. This is now a close-up, and what we can see is there are big stripes in the image, and these stripes appear to be this is in the pixel overlap zone, this region where we see the greatest amount of striping, but we also see their individual pixels which are causing problems. And at even higher scale, you can see there's a checkerboard artifact, and you can see there's some pixels running hot and some pixels running cold. Now, if we apply our recalibration at the pixel level, we see the result in the bottom figures, and a lot of the stripe noise has gone away and a lot of the checkerboard artifact is gone. There's still a little bit remaining. And this is where we use all of the data, the entire focal plane throughout the recalibration and remapping. And we do a nearest neighbor remapping of individual pixels to the geographic coordinates. Now, what happens if we change the remapping method from using the nearest neighbor within 200 meters of the target geographic coordinate, and we change that to be the median of the nearest neighbors that are within 210 meters of the target coordinate. And if we also drop one end of the focal plane, which has bad points, what's the result? Well, if we measure noise in the east-west direction, and which is basically a long track, and the north-south direction, which is a cross track, in our original data, in the long track direction, we had a 0.11 degree Kelvin noise level. And by the time we get to, if we just do the recalibration, we drop that to about 0.1. If we just drop the one end of the focal plane with the median mapping, we have about the same noise, and then it drops a little bit more when we add recalibration. If we use the, if we look at the crosstrack, we end up with with less decline. Our greatest noise was 0.08, and it gets down to about 0.05. So basically, this is a, we get a major noise reduction by doing all of this, by doing the combination of individual pixel recalibration and then changing the geographic mapping method. You can see the effect of this. If we try to calculate a Sobel gradient on this to try to find the edges of these features, a 3x3 Sobel gradient of the original image basically is uninterpretable. Our improved image, which uses both remapping and a change in the remapping and a change in calibration, we start to see we start to be able to resolve the edges of the various features. It's still not completely clean. There's still some residual noise. But then if we apply a method that Daniele Ciani came up with, the Holoborodko gradients, with a 7x7 matrix, we still get the same level of resolution of the features, but we now can detect the gradients. So we see this all as very encouraging, that the noise problems that we've seen in the data, the calibration problems we've seen with the data, we can fix those by using the hyperspectral sounders and by a relatively simple change in the geographic remapping. So what is our plan next? Well, one of the things that we are trying to do in this overall project is produce a GRIS compatible SST product. So in order to do this properly, we really need to finish our matchup of the IASI data from the period of record 2018 to 2023, and then fill in 2024. Right now, we've completed 2018, 2019, and 2023, but we've got 20, 21, and 22 that we're still processing. Our plan is to follow the G6 recommendations for calculating the correction coefficients and bias trends, and then generate both pixel and scene-based correction coefficients and the errors on those correction coefficients for months, quarters, and years, so that we can start to detect trends in bias. And then our plan is to test the quality of the corrections versus instruments like VIIRS, and which has a 750 meter pixel, and SGLI with a 250 meter pixel. And the plan is to add the final corrections to the ECOSTRESS L1B Radiance files of ocean scenes, add the corrected radiances, add the confidence limits on the corrections, and metadata associated with that, what time span and what reference satellite instruments were used. And then ultimately, the plan is to produce net CDFs with gridded geolocated corrected brightness temperatures, and test the SST algorithms using corrected brightness temperatures versus in situ, basically using the EQUAM database that NOAA is producing. And then at that point, we can start producing a split window ECOSTRESS SST that can match the various requirements of the GRIS community. So what kind of lessons do we learn from this whole exercise? Well, one of the major problems is that high spatial resolution comes with a big noise penalty. And the reason for this is that push-whisk instruments use a rotating mirror for cross-track acquisition. A long track, they have a series of pixels that are getting the data in the along track direction. But cross-track, everything is based on rotating the mirror. And the mirror has to rotate relatively quickly in order to image the swath that's wide enough for use with that's wide enough to be useful. So because of this rapid rotation of the mirror that's associated with very small pixels, the integration times by the sensor for the data for individual pixels get to be really, really short. And just like what happens when you try to take a cell phone picture at night, you get all kinds of speckle noise in a cell phone picture. The same thing is happening here. You have a very short acquisition time, so noise becomes very large in relation to the size of the signal. And there's no real way to fix this with the push-whisk instrumentation. You could do it with larger two-dimensional focal planes. In that case, you could do something like what the sounders do, which is stop and stare imaging, where you basically move the mirror to a particular place, grab a whole group of pixels, then and spend enough time getting those pixels that the noise levels are low, and then move the mirror to the next big block of 2D geographic area. But with basically one-dimensional focal plane on each waveband, you can't do that. So putting in the large two-dimensional focal planes would solve the problem, but they're too expensive for all of these future missions. All of these missions are constrained by funding, and apparently large 2D focal planes are ridiculously expensive. So we end up with high spatial noise. So this means that Trishna, SBG, LSTM, all of these missions are likely to have high noise levels. And it's just a feature of trying to get high spatial resolution in an instrument of this sort. So that's one lesson, and it's something we're going to have to deal with the future high resolution missions. Then the second major lesson is that focal plane non-uniformity is something that really does need to be corrected, and sometimes the standard method that's being used in the instrument, which in the case of ECOSTRESS is to image two different black bodies and then use the data from those black bodies to generate calibration coefficients. For some reason in ECOSTRESS, that's not really working completely. And so even though individual pixels have been separately calibrated, we still end up with non-uniformity. Now, part of that may be that there's some uncertainty in what the actual temperatures of the black bodies were. There may be some other problems that have to do with the geometry of the telescope, which lead to a fall off in radiation on one end of the focal plane. So there's various things that may be going on, but at least in the case of ECOSTRESS, the calibration method doesn't correct for those. So those non-uniformities, the spatial non-uniformities, lead to spatial noise in the image, which makes the image unusable for calculating things like temperature gradients for identifying fronts. Once you correct for those, then it becomes possible to detect the gradients by standard methods like the Sobel method. Many of the calibration plans for current and future instruments are based on in-situ calibration, using either buoys, drifters, or terrestrial sites that are specially instrumented for calibration validation. In all of those cases where you're using the in-situ data for calibration, we run into the difficulty that there's an atmospheric path which is going to influence the amount of radiation the satellite receives. If you do on-orbit calibration with a reference satellite, that problem goes away, because if the instruments are imaging the same location at the same time through the same atmospheric path, then the radiation received by both instruments should be the same. And the emissivity of the surface is the same for both instruments, so emissivity differences don't matter, or don't matter very much. And so so both of those reasons mean that presumably an on-orbit calibration with an instrument like IASI is very much preferable to the in-situ calibration method. The hyperspectral instruments do have noise, but because the method involves convolving the hyperspectral, the spectrum from the IASI instrument with the spectral response of the individual, in this case, ECOSTRESS channel, you end up using a large number of individual hyperspectral channels to generate the radiance estimate for a particular band in the ECOSTRESS instrument. And because you're combining many individual hyperspectral bands, the instrument noise is greatly reduced. So in these ways, on-orbit calibration with something like IASI is a great opportunity, and we hope that the Trishna, SPG, and LSTM teams will consider using reference instruments, specifically IASI or the next generation IASI, which has twice the resolution and half the noise. I hope that they'd use those instruments for radiance correction and homogenizing the data from these future instruments. So I think I'll stop there and start taking questions. Oh, one last thing. Thanks to John Mittaz for helping us figure out the decoding of the IASI files. And thanks to NASA for financial support via 2 different grants.